So this PowerPoint is going to take us through the concept of sound localization and balance. So we talked about the auditory inputs coming in. They kind of converge into the same locations. Now the idea is, how do we figure out where a sound is in space? And then also the other half of the kind of vestibular, the other half of kind of the inner ear is the vestibular system. So we'll talk a little bit about balance and how that works. So what is sound localization? That's the ability to recognize where sound comes from, right? So if you're playing Marco Polo, how do you know where your friends are? And you need to understand both horizontal and vertical location of the sound. So you've got different ways that you're going to interpret sounds that are coming in to understand where they are happening relative to both of your two ears. And that's going to work because we have that binaural, meaning two-ear convergence of information in the brainstem. So how does sound localization work? First off, it can work off interaural time delay, basically the difference when a sound hits both ears. So you're looking here on the right, you have sounds coming in from the side. It's obviously going to hit this ear first, and then it's going to get to this ear second. So there's going to be a difference in timing. You know, something straight ahead, there's going to be no difference in timing. If something's off to the right a little bit, okay, the right side's going to get there a little bit faster. So the difference in timing between the two ears will tell you kind of where in the horizontal space that sound is coming from. At higher frequencies, though, that's not quite good enough. So instead what it uses is a difference in intensity of the sound at both ears. So you can imagine that as a sound goes in the right ear, like in this case, say goes in the right ear, and then you get a kind of fainter version of the sound, either maybe a reflection or after it passes through the head, it's going to decrease in intensity, which is going to give you an idea of where that sound is relative to the other one. So when the same frequency hits the opposite ear, the difference in kind of volume level between the two ears will tell your brain can cue off that to figure out where that sound is coming at in terms of the horizontal axis. So for timing, one of the things that happens is you have a lot of cells in the spare olive that are frequency tuned and timing or intensity tuned, meaning that, for instance, here, the sound gets into the left cochlea first, so it's going to travel across, okay, and then it's going to come in from the right cochlea too, and it just so happens that at cell 3, for that timing, both of them hit here, and you get the maximum peak response. Whereas cell 1 might be preferential for something coming in from the right ear first, because the left ear has shorter to travel. The right ear has longer to travel, but in this case, cell 3 is the one that's going to respond to something coming in from the left, because that's the one that's going to receive it first. It's going to travel a greater distance, and cell 3 says, hey, that sound is coming from over here on the left-hand side of space. So the timing, the coincidental timing of the signals resulting in the largest amplification is going to tell the brain, hey, cell 3 is the one that we know where cell 3 is in the physical world around us. So how can we do vertical plane though? So we have horizontal axis, we're going to do timing and intensity differences between the two sides. In the vertical plane though, what we're going to rely on is actually the reflections inside our own ear. So your ear has a shape to it that's not just flat, it's not just an opening, it has this conical pinna to it, this pinna shape to it. And what's going to happen is sounds are going to be direct into the ear, like in path 3 here, and then you're going to have the reflected sound back off the pinna up at this point right here. Path 2 comes directly in, and then it's going to reflect off this part of the pinna and bounce back in. And based on the timing of when you get that little echo between the two things, the brain's going to be able to detect where in the vertical axis that sound is coming from. So it allows you to, because you're almost hearing the sound twice, the direct and the reflected sound, you are able to compare those two things to get an idea of how high or how low that's coming from. And then again, that's going to be based on the shape of your ear as to what the time is going to be. So that's kind of sound localization. A couple quick methods on how we do it, how it gets integrated into the system, how we're interpreting that information. Then we also have the vestibular system. So in the vestibular system, we have two major parts to it. We have the semicircular canals, which are these big things out here. You can see that there are three of them. And then we have the otolith organs, the uticle and the satricle. They're used by the body for balance, equilibrium, posture. Where's your head? Where is your head? Where is your head relative to your body? How is your head moving? And also for eye movement, for helping you track your eye movement as it's going along. So we'll see how these two different things work, and they actually work fairly similar to the auditory system. They use hair cells, okay, but different kind of setup because we're not dealing with sounds pushing on something. We're dealing with head movements. So in the otolith organs, the utricle and the saccule, you have this gelatinous cap sitting in here. Okay, you have these little otolith crystals sitting on top, and then you have the hair cells embedded inside that gelatinous cap. So what happens when the head tilts is these otoliths on top kind of get pushed backwards by the fluid. Okay, so there's the fluids moving this way as the head tilts up. And as that happens, those otoliths pull that gelatinous cap back. When they do that, just like we saw with the hair cells in the cochlea, the tip links get stretched, we get activity increases. So same kind of deal, anytime the head's going to move up and down, okay, or if you're accelerating forwards or accelerating backwards, it's going to be able to tell that because that gelatinous cap is going to move, it's going to shift those hair cells around, and it's going to send a signal to your brain to say, hey, we are moving in some direction or another. Our head is tilting, we are moving forwards or backwards. Now, it's not going to work at a constant speed, it only works if you are accelerating forwards. It helps you feel that. Helps your body sense that that's what's happening to your body. The other half, the semicircular canals, they are all about figuring out which way your head is rotating. So there's three of them. There's an X, Y, Z axis. And inside that semicircular canal, okay, there is this thing called the cupula. Okay? It is basically the gelatinous cap, okay, for the semicircular canals. You've got your long hair cells sitting inside it, with their cilia sticking up into that cupula. And then when the head rotates, say the head rotates to the left, the fluid inside is going to kind of move to the right because of inertia. It's going to want to stay where it's at. And since the head is moving, the fluid's staying still, the cupula gets bent. Those hair cells, the tip links again, open up the channels in the hair cells. And now you get activity levels, and it tells you, hey, your head is moving to the left. Your head is rotating in that direction. You have three of them because, again, we have the XYZ axis that we're taking care of. But that's the basic idea there. You're basically just using the resistance of the water, the fluid inside in that cupula to determine if the head is moving or not. So it's kind of a push-pull activation. So one side's going to get activated, one side's going to get inactivated by the push and by the rotation because you're going in opposite directions, right? And again, since you have one on each side of your head, there are three canals on each side. So that means you are kind of taking care of all the different axes of rotation that's possible for your head as it's moving along. Why is this? One of the reasons is really important. You got a lot of output for this whole vestibular system, modifying what's going on. One of the major areas are the extraocular motor neurons, kind of making sure your neck is turning in the right direction. Some of your limbs, so you can track those, make sure they're going in the right direction. But this extraocular motor neurons is extremely important because there's this thing called vestibular ocular reflex. And you could test this out. If you really stare at something and you try to rotate your head, turn your head back and forth, but keep staring at something, you can do it. Okay? You're not consciously moving your eyes. It's actually an ocular reflex that involves no brain thought, no conscious effort to move your eyes. It is purely just your muscles in your eyes are compensating for the fact that those semicircular canals are active. and it's going to activate the muscles there, right? As you're playing sports, it matters a lot. Your head's bouncing around while you're like running around, right? But you try to stay fixated, try to stay focused on something, and you can. You can focus on the soccer ball that's coming at you. You can focus on the tennis ball that's coming at you, despite the fact that you're moving and running. Your eyes will automatically adjust, even though the location of that object is changing relative to your body. So